Oh,
Yes,
wait
sir.
a minute. Nucleophilic substitution reaction. Okay. Only SN2 I had completed. So today I'm going to start the second part of nucleophilic substitution reaction, that is known as SN1. So are you aware of stereochemistry?
No, sir.
Okay. You are aware of isomerism, right?
Yes, sir.
Okay. So basically, when we talk about in 3D, there is another isomerism. You have heard of structural isomers, geometrical isomers, and optical isomers. Have you heard of optical isomers?
Yes, sir, I have.
So that is basically related to stereochemistry. So first of all, I'm going to start this B part of nucleophilic substitution reaction, that is substitution nucleophilic unimolecule. Substitution nucleophilic unimolecular. That is SN. Now see what happens here. Basically, in SN2, we have seen that that is one-step reaction. This reaction is two-step reaction. Two-step reaction. The first difference is SN2 is one-step single-step reaction, and this is double-step reaction. And now I'm going to show you, since they are nucleophilic substitution, so there will be nucleophile attacking on the alkyl halide part. CH3 whole thrice CBr reacting with OH minus, and it will give you CH3 whole thrice. And what happens? Br will be replaced by OH. Br will be replaced by OH. So C is here, and Br will be replaced by OH. So it will be OH, and now Br minus will be eliminated, substituted by OH. Are you getting my point?
Yes, sir.
So this is basically this reaction is not single step. This is double step. I just wrote the reaction in a single step. So now I'm going to explain the mechanism behind this. CH3 whole thrice CBr. First step, you can see what happens. I'm going to explain. This is a step one. This is a step one. So if I'm going to write the complete structural formula of this compound, it will be like CH3, CH3, and CH3, and Br here. Now, you know what happens here is very easy. Basically, this you can see this is tertiary halide. Br will take electron from carbon and it will form Br minus. Now, there will be positive charge on carbon because carbon donated its electron to Br. So it will be like CCH3, CH3, and CH3, and there will be pause. So in the first step, there will be formation of carbocation first, and in the second step, you can see this is CH3. I'm going to slide it down slightly. This is CH3. This is also CH3. This is also CH3, and in middle it is carbon, which is positively charged, known as carbocation. And now this OH minus will come into play, and it will attack on the carbocation because carbocation is electron deficient, carbocation is electrophile, and attacked by this nucleophile OH minus, and there will be formation of the product CH3 whole thrice COH. So please write this.
Okay, sir.
Let me know when you are done with this.
Sir, when do you
Yes,
think we will finish our syllabus?
the whole syllabus, right?
Yes, sir.
It will be finished by I think December,
Okay, sir.
before December. Okay. Yeah. If you want to finish that syllabus, finish the syllabus before that, we can have extra classes, and we will finish before that also.
Uh,
We can finish. Okay.
no, sir, actually.
Okay.
The speed is fine.
Okay.
Done, sir.
Very good. Now you can see there is formation of carbocation in SN1. That means there will be this is tertiary, then secondary, then primary. Can you tell me? I'm going to take example also of tertiary. That means this, of primary, sorry, secondary like this, and primary, that means basically like this. And with this bond, CH3 is connected, carbon containing compound, carbon containing group is connected. So can you tell me which one is more stable?
Sir, primary.
No. Do you know? Uh, that means you haven't studied well in class 11. And is there is there any problem in class 11? See, can you tell me if there is any positive charge? That means electron is rich, basically compound is rich in electron, or compound is rich in, sorry, poor in electron. Is it electron rich compound, or is it electron deficient compound? What do you think?
Electron deficient.
Electron deficient, that means it has less electron, that means it will be in need of electron, right?
Yes. Okay.
All the carbocation you can see are electron deficient compounds. Here all the electrons are, all the compounds are electron deficient compound, electron deficient. Now see, every C plus requires electrons. So this CH3 alkyl group has plus I effect. Alkyl group has plus I effect. Are you getting my point? Do you know what is plus I? This is basically positive inductive effect. Positive inductive effect. This inductive effect you have studied it in class 11. Inductive effect basically operates through sigma bond. Operates through sigma bond. So what does this inductive effect? Basically, inductive effect operates through sigma bond, and this is of two types, plus I and minus I. Plus I and minus I. This plus I donates electron to this plus I donates electron. The compound which has property of plus I donates electron and minus I is the if the compound has minus I property, that means it will withdraw electron. Are you getting my point, Aman?
Yes, sir.
Now see, this CH3 has plus I effect. That means it will donate electron. And you can see this CH3 is connected to a group which is electron deficient group. So this CH2 plus getting support of electron from one side. But this CH plus is C plus is getting support from two sides, and this C plus getting support from three sides. So which one will be more stable? Most stable. Can you tell me, Ayman? Madhya?
Yes, sir.
Which one is most stable? First, second, and third?
Sir, primary.
Primary. Okay. Okay. See, this is inductive effect. This is. Ayman, am I audible to you?
Yes, sir.
So can you tell me which one is more stable? Secondary, tertiary, primary? I explained just. Did you understand?
Sir,
Yes or no?
tertiary.
Tertiary. Okay. So Madhya, see, this inductive effect is of two types. This is plus I and this is minus I. It is property of any compound. So plus I, that means electron donating group. Electron donating group, and minus I, that means electron withdrawing group. Electron withdrawing group. Are you getting my point, Aman? Madhya?
Yes. Sir.
And you know what? If I'm writing plus here, can you tell me this C plus carbocation is electron deficient or electron rich? Can you tell me? Is it electron
Electron rich.
deficient? Electron deficient. That means it has lesser than its requirement. It has electrons lesser than its requirement. That means it needs electron. And you know what? This CH3 is has a property of plus I effect. That means it will donate some electron. This CH3 alkyl group has a property which donates electron. So you can see this CH2, this C plus is electron deficient, which will require electron. It is supported by one side, one CH3. This C plus is supported by two, and this C plus is supported by three. So this will be more stable than this. Are you getting my point, Madhya? So
Yes.
this will be the stability. Okay. So Madhya, we just started basically substitution nucleophilic unimolecular reaction, which is also known as SN1 reaction. This is double step reaction, two-step reaction. SN2 was about single step reaction, and the reactivity in SN2 is 1 degree, 2 degree, 3 degree. Now see, we have two-step reaction. In the first step reaction, this is step 1, and this in the first step there will be formation of carbocation. This Br will take electron from carbon, so there will be carbocation formation. And in the second step there will be attack of nucleophile. First write it, then I will explain it again, and we'll move to the next part. Let me know when you are done with this, Madhya. Madhya, are you done with this?
Sir, 1 minute.
Okay.
Done, sir.
Thank you. Now see, Madhya, you can see in the first step there will be formation of carbocation, and in the second step there will be attack of nucleophile, and then this reaction product will form. Now what I was explaining is that tertiary carbocation, secondary carbocation, and primary carbocation. In this, tertiary carbocation is most stable. So if we have order of reactivity for SN1, then 3 degree will be more reactive, 2 degree, and then 1 degree. Why? Because the intermediate formed of 3 degree is more stable. That's why 3 degree carbocation is more stable. Or you can say 3 degree halide also. Tertiary halide, we can write also tertiary halide, then secondary halide, and then primary halide. And at last, you can write CH3X, superprimary. And degree of SN2 is just opposite of this. Because of steric hindrance, that is single step reaction, there was no formation of carbocation. Is that clear?
Yes, sir.
Please do it and let me know when you are done with this. Let me know when you are done with this. Very good. Aman, are you done with this?
Yes, sir.
Now see, Aman, there is a point which is very important to write. Allylic and benzylic halides show high reactivity. Do you know why? Allylic and benzylic show high reactivity towards SN1 reaction, because the carbocation formed gets stabilized by resonance or through resonance, gets stabilized through resonance. If you have 3-degree carbocation or 2-degree carbocation, and if you have allylic group like this, CH and then CH2H, this will be more reactive. You know why? Because after taking electron from carbon, this allylic part, you can see this will be basically CH2 double bond and then CH and then CH2 plus. This will there will be conjugation of alkene pi bond and then carbocation. So there will be resonance. There will be a resonance, and due to this resonance, it will be more stable. Are you getting my point? That's why it shows high reactivity towards SN1 allylic. This is allylic part and this is benzylic part that I'm going to write. You can see this is a benzene which is connected with CH2X. After taking electron from carbon, this will be like this. I will show you the diagram also. Wait a minute. First write the above one, then I will write the resonating structure of this benzylic. Let me know when you both of you done with this.
Done, sir.
Very good. Madhya? Okay.
Done, sir.
Thank you. Now see, when we talk about benzylic, this allylic and benzylic, we already used this term in the beginning of this chapter. So just suppose this is, basically this is benzylic. You know that this is benzylic. So what happens after taking electron from carbon? It will be like CH2 plus. Now there will be conjugation. There is conjugation. You can see pi bond, double bond, single bond, and then vacant orbital, vacant p orbital. So this will move to here. Aman, do you know how to write the resonating structure? Yes or no?
No, sir.
Okay, Aman. So concentrate here. First of all, always remember that there are some conjugations. Only then we are able to write the there will be resonance if there is conjugation. Like if you have conjugation of double bond like this, double, single, there will be resonance. If there is no conjugation like this, is there any conjugation double, single, double, single, double? There is no conjugation, there will be no resonance. So see, double, single, and then carbocation, So there will be resonance. There are some conditions for resonance basically. Okay. So see what happens here. Do you know in one bond there will be two electrons? Yes or no? In one bond there will be two electrons. Madhya, do you know how to write the resonating structure? Please do respond.
Yes, sir.
Both of yes or no?
Yes.
Yes. Thank you. I mean, in one bond there will be two electrons because in one bond there will be sharing of two electrons. That's why in one bond there will be two electrons. Please do respond.
Yes, sir.
Okay. So so this electron, basically resonance is all about delocalization of pi bond. Delocalization of pi bond. So basically, whenever we have conjugation of pi bond or carbocation or lone pair or sigma pi bond, there will be delocalization of pi bond. Movement of pi bond will take place. So see what happens. This electron will be transferred to this. Will be transferred to this, and since this electron is moving to this, that means this bond will break. Yes or no?
Yes, sir.
Yes, this bond will break. So what happens here is very important to know. First of all, I'm going to write all this. Now see, if this electron is moving to this, that means this was already there. So this electron, sorry, this carbon has already positive charge and it is gaining electron from here, and it will get a negative charge. When an element gains electron, there will be negative charge. So it will have negative charge. Already there is positive charge, so negative positive will cancel each other, and there will be bond between these two electrons also. So that's why it will be double bond. And now you can see this carbon is donating electron to this. That's why there will be positive charge. Is that clear? Please make sure it's clear, because there will be a lot of question in organic chemistry that will be related to resonance. I'm waiting for your response.
Yes, I understand.
Very good. Now see, again there is two electrons in this bond. This electron will be transferred to this, so here will be positive charge. See, since this electron is giving its electron, so there will be positive charge, and it goes to this carbon, so there will be double bond. Now here it becomes the double bond, comes to this place, and you already know that this is CH2. So there was positive charge, and if this electron moving to this carbon, there will be negative charge. Already there is positive charge, and by gaining electron there will be negative charge. So this positive and negative will be cancelled, and this bond will be like this. Now again, what you are doing, moving this bond to this. So you can see this electron will be moving to this carbon. There is already positive charge. There will be negative charge because this electron is moving to that. So positive negative will be cancelled. Positive negative will be cancelled, and the bond will shift itself to here, and you can see there will be positive charge because it loses its electron. Now again, this double bond, you know that there will be two electrons, so this will move to this, and double bond will be here, and now again there will be CH2 positive because it just uh, gives its electron. That's why there will be positive charge, and it goes here, so there will be negative charge. Already there is positive charge, so positive negative will be cancelled. Now you can easily see that there the double bond, single double bond, the position of double bond changes. You can see there is two bonds, two pi bonds on the right hand side, and here the two pi bonds on the left hand side. So this is called resonating structure. This and this are same. Please do write it. Everyone done with this? Very good, Madhya. Aman, are you done with this?
Almost, sir.
Okay.
Done, sir.
Okay. Now we are going to start a stereochemical aspects of nucleophilic substitution reaction. Stereochemical aspects of nucleophilic substitution rates. You can see here, basically there are some terms like optical activity, chirality, retention, inversion, and racemization will be there. These stereochemical aspects are basically related to stereochemistry. This is a stereochemistry. And you know what optical isomerism is all about? 3D. Since we know that carbon is tetrahedral in geometry, that means the shape or geometry will be in 3D. And that's why there will be a concept of a stereochemical. So the first term that I'm going to use is optical activity. Optical activity. There are two types of compound. One is optically active compound and another is optically inactive compound. Now, how we are going to decide whether which one is optically active and whether which one is optically inactive? So see, there is an experiment we are going to perform to understand whether a compound is optically active or not. So we have basically unpolarized light first. We are going to focus on unpolarized light. These are all unpolarized light. And this unpolarized light, is going to pass through polarizer. This is an instrument that is called polarizer that makes unpolarized light polarize. That makes unpolarized light polarize. You will study about it in physics, wave optics also. So after passing through this polarizer, the unpolarized light becomes polarized light. And after this polarized light will be passed through a compound for which we are going to check whether this compound or substance is optically active or not. What we are doing, we are going to pass an unpolarized light or a light through a polarizer, which will make unpolarized light polarized light, which will make unpolarized light polarized light. And this polarized light will pass through a substance or a compound. This polarized light will pass through a substance or a compound. After this, there is another instrument that is basically analyzer. After passing through this compound, this polarized light either will rotate or not rotate. There is three probability. The first probability is like this light will not rotate. If the light is not this polarized light will not rotate, that means this is the compound is optically inactive compound. Again, I am going to explain. We are going to pass a light through polarizer, which will make the light polarized light, and this polarized light will pass through the substance and goes through analyzer also. This analyzer will show whether this substance or compound is optically active compound or not optically active compound, or you can say optically active compound or optically inactive compound. How we are going to decide? This polarized light after passing through this substance will either rotate or not rotate. If it will not rotate, that means this compound is optically inactive compound. And if it will rotate, then it will be optically active compound. Now it can rotate either in clockwise like this, and it can rotate either in anti-clockwise, either in anti-clockwise. First of all, if the light ray will rotate, that means it is optically active compound. For this, I'm going to write optically active compound. Rotate, that means optically active compound. Now if it will rotate anti-clockwise, anti-clockwise, that means that is known as basically levorotatory. Levorotatory. That is known as levorotatory, denoted by L or minus. And if it will rotate clockwise, if it will rotate clockwise, that means it is dextrorotatory. Dextrorotatory. That means basically this is denoted by either D or plus. Please write it. Let me know when you are done. Are you done with this?
No, sir, not yet.
Okay. Take your time. Okay, you are the only student here.
Done, sir.
Very good. Now see, we have some terms which we need to clear it out. First is basically chiral and achiral. So you can see from name, one will be opposite of other. Yes or no?
Yes, sir.
So what is chiral? First of all, we concentrate on carbon. Carbon should be, or carbon must be, of sp3 hybridized. sp3 hybridized. Carbon must have sp3 hybridized, and also carbon must have connected or bonded with four different groups. That means if carbon is attached with two same group, that means that carbon is not chiral carbon. That carbon will be achiral. Are you getting my point?
Yes, sir.
So if I'm going to ask you whether this carbon is chiral or not, can you tell me yes or no?
Sir, this is not.
Not chiral, because it is attached with four same group. That's why it is not chiral. Okay. So achiral it is. Please write it. Are you done with this? Let me know when you are done with this.
Yes, sir. Done.
I'm going to give you some questions. Identify chiral and achiral molecule. You have to concentrate on the group, not on the representation. That is only to confuse you. Okay.
Okay, sir.
Of the following pair of compounds. It is base and dashed structure. So basically, in the first, we have hydrogen here, CH3 here, Br here. This is the 3D representation, base dash, hydrogen, CH3, Br, and Br. The second question. This is CH3. This is also CH3. This is OH. And this is OH. In the second part of this is CH3. This is CH3. Hydrogen and OH. You have to choose from this 1 and 2, which one is chiral, and achiral, chiral and achiral. Please choose. And the third question, is very CH3, CH2Br, and then CH2, CH3, and with this, the pair is CH3, CH2, CH2, CH2Br. Please let me know. Can you solve it?
Sir, I have to choose between.
Yes, yes. Identify chiral and achiral. You just need to tell me which one is chiral and which one is achiral from the pairs.
Sir, in the first question, the first one is chiral and the second is achiral.
Okay. Because you can see BR same. That's why, right?
Yes.
Now in the second,
Sir, the first one is chiral.
which carbon is chiral in this? This is important. If I'm going to ask chiral, any carbon is chiral, that means chiral compound. If I am going to write, Ayman,
Yes.
this is alkane, and if one double bond is there, that means the compound is alkane. If one double bond is also if there is two double bond, this is also called alkene. So what I want to ask is, I'm going to number it: 1, 2, 3, 4, 5. How many centers? Chirality center of chiral?
Sir, one,
One. Which position?
two.
Very good, because this is OH, this is H, this is CH3 different group, and this is also different. That's why. If you are going to count this, you can see three hydrogen. That's why. If you are going to this, see this, it will have two hydrogen. It will also have two hydrogen. What about this?
Sir, at the third carbon.
What?
At the
1, 2, 3. Third carbon. So is it chiral or achiral?
it's achiral.
Achiral. So why you said at third carbon? What you wanted to say?
Because other than H and OH, the two
Group are same.
yes, sir, the two groups are same.
That's why it is achiral. Very good. Now come to the third question.
It's, sir, they're both achiral.
So wrong. Not both. If you are going to see, this has three hydrogen, two hydrogen, two hydrogen, two hydrogen. How can it be? If you are going to see this carbon, Br, hydrogen, hydrogen. Wait a minute. I'm going. Can I change the slide?
Yes, sir.
Okay. Now you can see. First of all, I'm going to write the structure of this. So can this carbon be chiral? The left carbon.
No, sir.
Can the second carbon be chiral? Third carbon can be chiral. Fourth carbon. All carbon have almost some groups which are similar or same. Yes or no?
Yes.
So this is a chiral. What about this? So see, if I'm going to write the structure of that, the first carbon has three same groups, that is hydrogen, and then this is hydrogen, this is bromine, this is carbon, this is hydrogen. This is basically chiral. You know why? Chirality is at this point because this is another group, hydrogen, bromine, CH3 and then C2H5. So this is chiral. Got it?
Okay, sir. Yes.
Please write it. Are you done with this?
No, sir.
Okay.
Yes, sir. I'm done.
Very good. Now see, we have another term that is enantiomer. Enantiomers. So basically, what is enantiomer? I'm going to define it first, then we will see. The stereoisomers, the stereoisomers related to each other, related to each other as non-superimposable, non-superimposable, non-superimposable are called stereoisomers. Non-super imposable mirror image, mirror image are called enantiomer. So if you are going to take a mirror image of a compound, and then if they will not superimpose each other, that relation is called enantiomer. If I'm going to take an example, if we have this OH and there is CH3 and then we have CH3 again and then we have H. This is propane 2. this is propane 2O. And if you are going to put a mirror here, there will be mirror image of this compound. Left will go to right, right will go to left, left will go to right, and right will go to left. This will be CH3. Now this is CH3, and also this is H. Now if you are going to rotate this mirror by 180 degree, so again we will get the same compound. Again we will get the same compound. This is CH3, this is CH3, and this is H. Now what I want to say is that this is A, this is B, and this is C. And you can see this A and B is not superimposable. These are not super impossible. If you are going to take one compound and you are going to superimpose with this compound, it will not be superimposable. That means enantiomer. A and B are enantiomers. Are you getting my point?
Sir, what is superimposable?
That means, see, if you are going to coincide, this is coincide superimposable. Yes or no?
Yes, sir.
Is it superimposable? This thumb is
No.
going to little finger. So if you are going to just see, focus on B, focus on B, you are going to take this compound like this, and if you are going to put it on the A compound, will it be superimposable? No. Why? Because CH3 on the left hand side and here the CH3 on the right hand side.
Okay, sir.
Are you getting my point?
Yes, sir.
So if you are going to take this and going to put it on A, the CH3 is on the right hand side and CH3 in A on the left hand side, they will not be superimposable. But if you are going to superimpose A and C, if you are going to take C and going to put it on A, it will be superimposable.
Okay.
Are you getting my point?
Yes,
So
sir.
A and B are enantiomers.
Sir, so no carbon or hydrogen, like not a single one should be superimposable.
No, basically not superimposable. There will be superimposable. Like if you are going to rotate or something, do like, then it will be superimposable.
Okay, sir.
But directly it will not be. Let me know when you're done.
Yes, sir, done.
Very good. Now going to take another example of this mirror image. This is OH. This is we have CH3, and this is basically C2H5, and this we have. This is butane 2. Butane 2. If you are going to keep a mirror here, there will be mirror image of this compound. So you can see left will be looking in the right. This will be C2H5. CH3, hydrogen, and then OH on the right will be looking at left, seeing at F. So see, this is D, this is E. And if you are going to rotate this with 180 degree, with 180 degree, so it will be again, see what happens here. This C2H5OH will move to dashed, and this CH3 will move to solid wedge, and now this. Now you can see this representation and this representation. Now this DEF, D and F is not superimposable. D and F is not superimposable. Please write it first, then I will again explain it.
Okay, sir. Done, sir.
Very good. So you can see basically in the previous question, at the place of CH3, there was C2H5, there was CH3. So CH3 either stands here or here, it will be same. So after rotating at 180 degree, it will change its place. But if this both are same group though, so it won't affect. Since now the group are different, so C2H5 will take place of CH3 and CH3 will take place of C2H5. Now you can see this will not be superimposable with this. That means they are enantiomers. Is that clear?
Yes, sir.
Now I'm going to give a question. Arrange the compounds of each set in order of reactivity towards SN2. The question is basically 2-bromo, 2-methyl butane, 1-bromo pentane, 2-bromo pentane.
Sir, 1-bromopentane, 2-bromopentane, and then 2-methyl butane.
Wait a minute. Methyl butane, that means 4 carbon, and it will be 2-bromo and like this, and 1-bromopentane, that means like this, and 2-bromopentane, that means like this. Oh, pentane it is, and 1-bromopentane. So which one will be? This is A, and this will be B, and this will be C.
Sir,
Most reactive, this, right?
CBC. Yes, sir.
Yes. Very good. The B is 1-bromo, 3-methyl butane, 2-bromo, 2-methyl butane, comma, 2-bromo, 3-methyl butane. So you are going to arrange this in increasing or decreasing order of SN2 reactivity. Can you solve it? Methyl butane, that means 1 bromo and 3 methyl. 2 bromo, 2 methyl butane, that means this. 2 bromo, 3 methyl butane. Wait a minute, I just did a mistake. 1 bromo, that means this is Br. Now 2 bromo, 2 methyl, that means this is Br and 3 methyl. So this will be like this. So the most reactive, I'm going to write A, B, C. So the most reactive group will be A. This is 1 degree, this is 3 degree, and this is 2 degree. So A, C, B. Yes or no?
Yes, sir.